Okay, good morning. Good morning. Hey, Sandra. Hey, good morning. Good morning. How are you doing? Fine. How are you doing? Fine. How are you doing? Okay, good. Okay, let's start. This is my first time to give a lecture without slide. I will try. And you went through lesson 1 to lesson 8, so all of you are now very familiar with how to design your circuit. And yesterday you also learned what kind of measurement device we have. So today we are studying how to measure the device that you design. Okay, the power, ground, and recovers. When you measure a device, you need many kind of power supply. So you need power supply for your LSI, and you need power supply for measurement device. You need power supply for your power supply device. So you need many kind of power supply for a plug. And let's say we have this kind of plug, and I'm sure you will use this kind of plug for measurement. And there is another plug, this kind of plug. For example, let's assume this is a plug. And the plugs, the voltage applied to this plug means the voltage between this node and this node. And voltage to the another plug means the voltage between this node and this node. So the ground level between two plugs are different. So when you apply, the power supply from this plug to your device, and apply from this plug to your oscilloscope, the ground line is different. So even though there is no signal between the chip and the oscilloscope, you will see some kind of waveform on your oscilloscope because the ground is not common. So when you use many power supply from plugs, you have to use big plug with the same ground voltage so that all your devices have the common ground. That is very necessary. And the next page, the power source and the decoupling capacity. And we learned that I'm sure once you start your measurement, you will suffer from power supply noise. And there are many ways to suppress the power supply noise. And the reason to have your power supply noise is that all your power supply lines come with resistance and inductance. So all the lines come with resistance and inductance. So you want to cancel those impedance. So in order to cancel it, you use capacitance. Once you have capacitance, the current, AC current, is going from the capacitance, not from the power supply through the inductor. So that you will see less dIdt, and you will have less noise. So decoupling capacitance is very important. So once you design your PCB board, you have to put many capacitors on it to stabilize your power supply. The next one, the parallel connection of decoupling capacitor. The decoupling capacitor works fine to reduce the power supply noise. But usually, the capacitors have kind of lines between terminal to the capacitor itself. And again, all the lines come with resistance and inductance. So even you buy a capacitance and try to put the capacitance on the board, the capacitance itself has inductance. So on a symbol, you put capacitance on the two node, but that capacitance always comes with inductance on the both terminals. So that means the capacitance has LC resonance. And that resonance frequency, of course, depends on the capacitance value and inductance value. So in the figure, ideally you have your frequency and impedance. In the capacitor has less impedance on the high frequency because the impedance is J omega C over 1 over J omega C. So for the higher signals, it's less impedance. And for very, very high speeds, the C looks like so. And on the other hand, L has higher impedance as frequency goes up. Because the impedance of L is J omega C, J omega L. So you have so the impedance is becoming smaller as frequency goes high for let's say we have this kind of circuit. And in that sense, the impedance is getting higher as frequency goes high. And at this point, we have a resonance frequency, and actually the total impedance of these two elements is coming like this. And we call it resonance frequency. So, for power supply noise suppression point of view, we want less impedance on the power supply. And ideally, we want zero impedance on power supply. But however, the line always comes with capacitance, resistance, and inductance. We cannot make zero impedance. So we put capacitance and we want more lower impedance. So in order to do that, we want to put larger C. The larger C will go down the impedance, and smaller L will go down to the inductance like this. Large C and small L. We want large C and small L. And however, anyway, we have this kind of resonance frequency. So after the resonance frequency, the impedance is getting higher. So, and we will have the noise around this frequency. So we don't want this happens. So will put so here we will put another capacitance. This is C1 and this is C2. So this curve is coming C1 and L1. This curve comes with C1 plus L1. And when we put C2 in parallel with C1, we will have another characteristics, C2 and C1. And the total, another column. So the total impedance of those two capacitors is becoming like this. And so that we will have smaller impedance for the wide frequency range. So in order to realize that, we will put many capacitors with different capacitance value. So usually maybe I will talk later, but usually I will put 1 microfarad and 100 pico. 1 micron farad, 10 nanofarad, 1 microfarad, 10 nanofarad, 100 picofarad. I will put 3 capacitors in parallel for the power supply. In order to have this kind of impedance characteristics, so we will have 3 curves like this. So, the first time, if you see that. Okay, I put 1 microfarad, 10 nanofarad, 100 picofarad in parallel. That is equivalent to put this number of capacitance. So, and it doesn't matter if you have 2 microfarad, it's okay. But it looks okay, and it is okay if there's no inductance. Put one large capacitance is okay if there is no inductance. But there is inductance, so putting many types of capacitor works very well. So when you design your PCB board, you have to put many types of capacitance on power supply to stabilize your power supply. And another topic is about return bus. And usually we draw the line, for example, for inverters. And we see that the current going this way or this way. And however, the signals, once we go, the signal goes, another signal has to come back. And so the current always loops. So when the current goes, some current in the same amount of current has to come back. So in this picture, when current goes in this direction, we often draw this kind of pictures. The current goes from inverter 1 to inverter 2. What happened here? Oh, okay. The current has to go in the loop. All the current go into the loop. So once current goes, the same amount of current has to come back. In this way, the current from inverter 1 to inverter 2, there the current from here to here. How the current come back? Okay, so we have power supply and ground, and power supply and ground. And actually, this power supply means a power supply and ground. So when the current goes here, and this current is mainly from power supply, and this current is going back to this through ground. So we want to make sure the current always goes into the loop, and how the charge, where does the charge coming from and where the charge is going to. So when we charge the inverters, usually the charge is going from the power supply to the inverter plus terminal. And at the same time, the inverter minus terminal, from the inverter minus terminal, the same amount of charge is going into the ground. So when we discharge the capacitance, the plus plate of the capacitors, the charge is going into the ground. And at that time, the same amount of charge is going into the minus plate to the capacitors. So when we charge, the current is going from the power supply to the charge. And when discharged, there's no current from power supply to ground. It's just a charge recycled from the plus plate to the minus. And the return pass 2, let's say the inverter, there's a charge from inverter 1 to inverter 2. In this case, the charge is going into here, and this charge is going into the PMOS and NMOS. And in this charge, it's going to go in back to the power supply, and this charge is going back to the ground. So usually we think that when the first inverter drives to the next inverters, and next inverter is terminated to ground usually when we model it. In this case, the charge, all the charge is going into the capacitor and all the charge is returning into the ground. But actually, part of the charge is of course going into the ground, but part of the charge is going up and come back to the power supply. So the amount of charge from the power supply to the ground is different between this and this model. And you have to be careful. And the return path 3. and return path 3. And usually the ground line between this signal Y and ground line are usually located very close. But once you have very, once there's a very, this kind of, the ground line is located very far. In this case, the ground line is far, so the return path is going to this way. In this case, there is a current loop on here. So this is the current loop area. And the inductance value is proportional to the loop area. So once you have this kind of large loop, you will see large inductance. So in this case, you will see inductance here. And it will degrade the performance. So the point here is that we should have to take care of the return path. And the loop area should be small in order to reduce the inductance. Otherwise, you will have inductance and it will degrade the delay and degrade the performance and it will induce the noise. You will suffer from it. So once you suffer from inductance, you will check if there is a large loop. And for your measurement, you always have to take care of how the signal returns and make the loop area as small as possible. And that's it, return path 5. Return path 5. L is proportional to area, so we have to reduce the area as small as possible. And connectors. So when we measure the device and we have to connect the measurement device with your LSI chip. And maybe you mount your chip on the board and there's a board, you use many kind of connectors. And for connectors, we have many types of connectors. So we want to use many kind of connectors as you want. So the first one is header pin. And header pin is, we can have many number of pins in the same area by using header pins. But the header pin can only slower signal can go through the header pin. And usually about 100 megahertz. And less than 100 megahertz, you can use header pin. But above 100 megahertz, you have to use another high-speed connectors. And the high-speed connectors also have many kinds. We have BNC, SMA, 3.5 millimeter. And usually the BNC, it's the upper limit is 1 gigahertz. And for SMA, we can use SMA around 10 gigahertz. And 3.5 millimeter, maybe 20 gigahertz, and 3.4 millimeter, we use 50 gigahertz. And recently, you may use 1.85 millimeter, which can be used until 67 gigahertz. So there are many kinds, and the higher frequency ones are expensive if you buy. So in this case, we put a picture, and this is just a and we have many converted from BNC to SMA or SMA to 2.4 millimeter and 2.4 millimeter to 1.85. And usually in our laboratory, we often use SMA cable. SMA is our standard. But we use 2.4 millimeter only for up to 20 gigahertz meter. So, and 2.4 millimeter accessories are expensive. And for example, these connectors, maybe BNC connectors, maybe you can buy $1 but for by BNC connectors. And the SMA connectors, maybe $10. And SMA connectors, $100. And 2.4 millimeter, $300. So maybe you want to measure as lower price as possible, but you have to be much care of the performance. So for slower digital signal, you will use header pins, and for RF signals, you will use SMA or 2.4. And also we have many types of cables, and we have the header pin cables and 2.4 millimeter cable, SMA cables. And here we learned that we will use 50 ohm system impedance. So SMAs have 50 ohm system impedance. So the SMA cables has 50 ohm characteristic impedance. But for header pins, because the header pin does not care for the high speed, so the characteristic impedance is not decided. But above SMA, the system impedance is 50 ohm. And SMA cable, and this is a very high-speed cable, so this has to be very stable. So, and when the current goes, and same amount of current have to come back. So the SM cable, there is a center lines and there is a shield lines, and the center line is the signal, and it is surrounded by a ground line. So SMA cable has two ways. The one is the center line which signal goes, and be surrounded by a ground line. So once you connect the device A and device B, we have to care. We also have to care not only the signal connections, but also we have to care about the ground connections. So the SMA cable always comes with the signal and ground, so that you have to be much care about the ground connections on SMA cable. And also we have many kinds of accessories. And in these pictures, it shows the alternator and 20 dB alternator, 6 dB alternator, blocking capacitor, and bias B, and dividers, and open termination, short termination, and 50 ohm terminations. And you will use this kind of accessories once you start your RF signal. And in order to use these accessories, you have to know what is inside. The next page shows the alternator circuit. In alternator, it will alternate the input signal. So 20 dB alternation means the voltage is becoming 1/10. and 6 dB means the voltage becomes up. So the point of the alternator is that the input impedance from the alternator should be 50 ohm. But the output voltage has to be, for example, higher for 6 dB alternator. So the input voltage always be 50 ohm. And it will have alternations. So actually the alternator is just a resistance ladder, like shown in the slide. And let's say we have resistance R1 to 3. And the input impedance D0 should be 50 ohm. So once you want the alternation coefficient, you can calculate and you will have how many resistors we will have. So in this case, let's say for minus 6 dB alternator, its alpha value becomes 1/2. And the alternator is often used at the input terminal of the measurement device. For example, in your high-speed oscilloscope, it usually limits the Vmax and the mean voltage. And let's say we use 1.8 volt VDD for I/O. So the signal swing is from 0 to 1.8 volt. But the oscilloscope input voltage, especially for the high-speed oscilloscope, is very sensitive. So the input voltage is limited between 0 to, for example, 10 millivolts, or 0 to 500 millivolts. And I haven't seen the high-speed oscilloscope with 0 to 5 volts. So in such case, you put alternator on the oscilloscope input terminal to make the signal, for example, 1/10 of the voltage, so that the oscilloscope can read the signal. And another one is a blocking capacitor. And this is also often used. And the blocking capacitor is just a capacitor, just a large capacitor. So that it will, for the large capacitors, the impedance becomes 0 for AC signals, and the impedance becomes infinity for DC signals. So for the blocking capacitors, it's cut off all the DC component and pass through the AC component. That's a blocking capacitor. And it's also used for measurement, input terminal of the measurement. For example, for spectrum analyzers. And the input of the spectrum analyzers are also very sensitive. And what we concern for the spectrum analyzer is frequency component. So DC component, we don't care about it. So we only consider the AC component and frequency component. And also it has a very sensitive, so higher, so the maximum input voltage is limited. So in such case, we put DC blocking capacitor to block the DC, and all the signal is come down around 0 volt, so that it will protect from the damage for the measurement device. And the other one is bias D. This has a reverse function of the blocking capacitor. The blocking capacitor will remove DC component, and bias D will add up DC component. And for AC signals, C means short and L means open. And for DC, L is short and C is open. And for AC, C is short and L is open. So with this kind of connect C and L, like T curve, we can add up a DC component on the AC, on the coming AC sequence. So the input is AC, whose DC voltage does not matter. And the output is the incoming AC component plus applied DC component. And also we will have power splitters that will split the input signal into two parts. And this is also, we often use this for measurements. For example, and we sometimes want to see the waveform on the oscilloscope and want to see the waveform on the spectrum analyzer at the same time. At that time, the output is input to the divider, and divider output, one of the output is to the oscilloscope, and one of the output is to the spectrum analyzer. And of course, the power from the input is the same, so the power for the terminal 1 and terminal 2 are becoming half. But the important thing is we can measure the same signal in different devices. We will use it. And here, the power splitter. In the power splitter, the input impedance also have 50 ohm. Otherwise, we will have reflection on the terminals. So we don't want reflection to happen. So the input impedance from the input node should be 50 ohm. And from the output terminal, we will use 50 ohm SMA cables. So the dividers, we have 50 ohm impedance in parallel. Then connect to the 50 ohm. So from the input terminal, it will have two 100 ohm terminations, and that is equivalent to 50 ohm terminations. And the terminators, and we have open terminator and short terminator and 50 ohm terminator. And for open and short, we seldom use open and short, but we often use 50 ohm. For example, when we have multiple output devices, for example, 8 output devices, and we want to measure all 8 terminals, but the oscilloscope input terminal has only 4. In such case, we connect first 4 terminals into the oscilloscope, and the other 4 terminals, when it's leave open, the operating condition is different from the real actual operating condition. So in such case, we put 50 ohm terminator on the last 4 terminals. And then we replace them and measure the last 4 terminals on the oscilloscope, and the first 4 are terminated by 50. So we often use 50 ohm terminator, and we have many terminators. And the next one is blower. When we design, for example, RS, especially RS or very high-speed output circuit or high-speed input circuit, if we assemble the chip into the package, and package have a bonding wire and lead frame, and bonding wire and lead frame always come with inductance. So its performance will completely change. So we want to connect the pad by 50 ohm system impedance as close as possible. So the prober has a 50 ohm system impedance at the top of the pins. So from the here, so in this case, at the top of the needle, and there is a connector, this lines are designed by 50-ohm system impedance. And these are SMA connectors, so SMA cables are attached to the connectors and connect to the, for example, oscilloscope. So from the oscilloscope input terminal to the top of the needle, we can have a 50-ohm line, so that it does not disturb by the connections. So for very high-speed signals or RF signals, we have to use the prober, not on-board. And this prober is also expensive. And this blue one, this blue prober, this means we have 5 needles, and we have 2 signals surrounded by 3 ground. So you say GSGSG, means ground signal, ground signal, ground. So that we will have the rejumpers from the signal to the ground. So for GSGSG, and we have 2 signals with 5 ground, and the SMA terminals, we have 2 terminals, which has 1 signal surrounded by ground. So SMA, the SMA connector, the center is signal and surrounded by ground. So GSGSG, and this prober cost about $30,000 for 1 probe. 3,000 US dollar. Okay, $3,000 for this blue one. Maybe more expensive than your monthly salary. So this is very expensive. And the next one, the yellow one, the gold one. And this is, as you can see, there is a header pins, not SMA connectors. So this is used for low speed signals, or this is used for power supply. And this is relatively cheaper than the blue one, but still this is expensive. And when we measure our devices by using this prober, the next page, before touching to a real device, we have to adjust many things before touching to your real device. And we call it just a pin contact. So there is in the right figures in the circle, and we have this around this side. There is a plate, and white plate, and there is the surface is a gold. And we use that plate and see on the, and first, before touching to a real device, we touch on the gold surface first, and then make a scratch to check if the prober is on the prober is on the flat, When the prober is adjusting like this, when we make scratch, you will see only several scratch. But when it is completely flat, you will see all the scratch on the pins. So before that, your device is more and more precious than the gold plate. So before touching your real device, first you will make your prober works correctly on the testing board, and then you will touch on the real device. And when you measure by probing, just probe it. But when you design your PCB board and assemble your chip on the PCB board, you have to put many kind of capacitors or connectors and etc. etc. And in that case, you have to know what kind of assembly parts we have. And this picture shows some kind of parts that I often use. The first one, electrolytic capacitor. And this capacitor, the capacitance is very large, but it has less loss. And it works only for lower frequency. And it has very large inductance on the wires. And also the content of this capacitor does not have high frequency characteristic. So we can use this only for low frequency signals. And the next one is a chip capacitor. And the capacitance value is relatively I have the slide for this type of capacitors, we have large capacitor from nanofarad and microfarad or millifarad. But the frequency response is not good. And also we have a polarity. So the longer terminal should be plus terminal. And shorter terminal should be on the minus terminal. And this is a chip capacitor. It has the capacitance is smaller compared with this type of capacitors, but it has good frequency response. so for the power supply, I told you that we have to put many types of capacitors. So we use this type of capacitors and this type of capacitors in parallel together. So that we will have the small impedance for wide frequency range. And this is a chip capacitor, and it's the size. We have many sizes. And we have 1 millimeter and 0.9 and 0.5 millimeters. And for the recent cellular phones, when you design cellular phones, we want to make more smaller PCB board. But when you assemble this capacitor by yourself, at that time, the smaller capacitor is very difficult to handle. We will use inset to handle it and solder and make heat to attach to the board. So if you use very small chip capacitor, it is very difficult to handle. So I recommend you to use relatively larger one, larger than 1.5 millimeter. So I often use 1.5 millimeter chip capacitor. And it does not show the capacitance value. And this type, we can say this is 470 microfarad. The capacitance value are printed on this. But for this one, it often says 104 or 105 or 202. Only 3 digit numbers on this chip capacitor. So that means 104 means 10 times 10 to the 4 picofarad. So 105 means 10 to the 5 picofarad, and 254 means 25 to 10 to the 4. So from this number, you have to calculate the capacitance value for this. And also we have the chip resistors. And there are many kinds of chip resistors, but usually when we measure our LSI, we seldom use resistors. The one thing we use the chip resistor is for 50 ohm combination. So in our lab, we have 50 ohm resistors, many pieces of 50 ohm resistors, and we don't have 10 or other than 50, we don't have any chip resistors. We have only 50 ohm chip resistors. And also it shows 501. The number 501 is 550 times 10 to 1. So we only have 501 chip resistors. And this is the SMA connector. And we will have this AU cortex one, and there are several types of SMA connectors. But when you buy SMA connector, you have to buy the SMA connector coded by gold. Coded by gold, and it is easy to handle the AU coded SMA connector. And also we will have a shield loop. And this is a picture of the shield loop that our laboratory has. This is the shield loop 1, and we can get inside here. This is the desk and table. And this is 2 meter high. This is the shield loop. And another type of shield loop is this. We have only a small probe station inside. And when we set up there, and after setting up, we will close the shutter and measure. And actually, this type of shield, the shield is not good enough. So the easy test for the shield is just put your cell phone inside the shield and try to hold it. when I experiment that, I cannot call to into this shield, but I can call into this shield. So when we do a very, very, very precise measurement, we will use this shield. But usually, when you design your chip, the chip operation environment is around this type of environment. So if your chip operates only in shield, that means your chip does not work in real atmosphere. So you have to make sure that while you are measuring your device in the shield, you need to have very special requirement or special reason to use shield. And actually, this shielding does not work well. And I tried something, and this is aluminum foil. You can buy this in the supermarket, just $1. This is aluminum foil. And put the aluminum foil on this, for example, this kind of box. Shield the box by this aluminum foil. It actually works fine. So if you want to have very instant shield box, just buy a box, plastic box, any box is okay, just buy a box, and use this aluminum foil to make it shield. That works fine. And this is an example when I measure my knowledge. And this is we have a board like this size, like A4 size. The surface is covered by cardboard, and mainly it is FR4. So FR4 board, and the surface is covered by cardboard. And we use that kind of board here. And there is a machine that will scratch, and the rotating needle will write a pattern on the board, so that only copper parts are scratched out. So here, you can see that there is an island around here, and there's an island around here, and there's an island around here. So the other things, this is a ground plane. And there is we scratch to draw an island like this, so that this island can be connected to the power supply, so that we have a power supply island. And on that island, because this is a ground line and ground and power supply, and ground is attached on the ground plane, and the power supply is attached on the power supply island. And only this island has VDD. And this island is connected to the VDD pin of this package. And here, in order to stabilize the power supply, we want to have ideal power supply island. And at the end of this line, we will have an ideal power supply. But we have a very long wire and which has a very big inductance. So this performance, this island is very noisy. So we want to stabilize this island. So we put many types of capacitors on this island, between this island and ground. So for example, here you can see that there are several chip capacitors here. And as I told you, I put the 1 microfarad and 100 nanofarad, 10 nanofarad, 1 nanofarad, many types of capacitors in parallel, so that we have a small impedance for wide variety of frequencies. And for high-speed signal, coming from here. So and this is our SMA connector here, and this is also a 50 ohm transmission line. So we can buy these types of connectors, the SMA connectors with 50 ohm transmission line. And at the end of the transmission line, the center is a signal and it is covered by ground. So we have kind of a work to just put the signal out. And that center signal is attached to the pin, signal pins. And it's surrounded by the ground, and ground is connected to the ground plane. So in this case, we use this kind of 50 ohm connection only for clock. And other one, and for power supply, we put power supply island here, and we put many types of capacitors. And for DC signals, for example, this is the selector. It just selects the mode, for example, high speed mode and low speed. And we don't have to have a high speed switch. In this case, this is just a DC signals. So we just connect here. And of course there is an island, but we don't put any capacitors because this is DC and no current flow. And let's say we have to take care of the return path. For the clock signals, the center is the signal line and covered by ground, and the ground becoming a return path. And for power supply, the red line are power, and ground line is the ground. So we will have the current from the red line is coming back through this black line. And in order to reduce the resistance as small as possible, the red line and blue line are always pairs and twisted. And this is another example. And we use SMA cables for high-speed pins. And this time, we measure this signal from the pin. And when I measure this one, this signal is not so high frequency. This is about megahertz or about 100 megahertz. So we don't have to use SMA. We can just use this kind of probers. And this prober is connected, and actually we don't know about the characteristic impedance of this prober line. And when we measure this, the oscilloscope is in 1 mega ohm, not 50. And here is another example. And in this time, the frequency is not that high, but it's about several hundreds of megahertz. So in this case, we don't have to use this types of 50 ohm line to the tube. So here, the 50 ohm is guaranteed until here. But in this case, 50 ohm is guaranteed until here. And actually, I don't know the system impedance on this line. But this is enough because this is several hundred megahertz. So if the signal is gigahertz, you have to take care of this line with 50 ohm. But in this frequency, you don't have to take care of 50 ohm line. So we put this is SMA connectors on the board and connect it. we input clocks from signal generator. And signal generator, its output is around ground line. So signal generator output is around ground and plus 1 volt and minus 1 volt, plus 1 volt and minus 1 volt. But usually the clock input requires ground to be. So we want to add up some kind of DC voltage from the signal generator. So here we, from the signal generator output, we use bias D. So by using the bias D, we have AC signal from signal generator and apply actually half VDD of this. So I use same symbol as the different voltage. This is VDD and this is half VDD. By using half VDD, we apply here and input the input buffer. And this is another example. So at this time, we use many control pins. So this time we use header pins here. And for clock, this is a high speed, so we use SMA connector. So only clock is used by using SMA, and another control signals are getting into through header pins. And also we put, this time we put only this electrolytic capacitors. And we don't use chip capacitors here. And because this chip does not require stable VDD. Actually, at this time, I wanted to measure some kind of power supply noise. I want to measure the power supply noise, and I want to measure the effect of power supply noise. So we don't want to have stable power supply at this time. So that's why I don't put chip capacitor here. I just put this kind of large capacitors. And this is another example. This is a very high-speed measurement. So we directly plug on the chip. We don't assemble the package. We directly plug on the chip. Here, this is the picture. And these two signals are, I don't remember the signal, but we have two input and two output. And there are two high-speed input and two high-speed output. And another control signals for power supply are supplied from these two probes. And we can see that this gold line is for low speed. And so when we supply power, we want to have more stable, we want to give more stable power supply. So here, we put a kind of header pins on header pins. And we can do some kind of manufacturing by ourselves. So this is power supply, and this is ground. And I put capacitance between this red line and black line. And we don't want to directly put capacitors on these probes, because many people use the same probes. So if you want to apply more stable, you have to make this header pins by yourself and make a kind of work to make a stable power supply or make a stable control pins. And another topic is GPIB control. When you measure your chip, maybe you will use many types of measurement device. For example, this is the chip, and we use power source, real-time oscilloscope, and logic analyzers. and we control many devices at the same time. So in this case, usually all the device has communication ports. And this is the power source, and they have a communication port like this. And this is called GPIE. I don't know what that is, but we call it GPIE. And we, from the program, we can send a command to here to control the output. So from the, this is a PC and this is a display, and the PC is connected to all these devices through GPIE cables. So from PC, we will send a command to, for example, set 1 volt to the output, or set 0.9 volt to the output, and set what kind of logic we have to have. And once we go into a measurement room, maybe 80% of time I spend in front of a computer and writing a C program. I usually don't touch to these measurement devices directly. I always control the measurement device through program. Because once you start a measurement, you want to sweep something. For example, you want to sweep power supply. 0.9, 0.95, 1.0, 1.05, and 1.1. So if you want to manually change and measure it, change and measure it, push button and push button and push button, when you want to sweep and you want to do many types of measurement, your measurement result will not be beautiful. And by sweeping everything from computers, you will have beautiful results. So I strongly recommend you to this. Measurement is almost equal program. So this is how we measure output. Any questions?
So in your scale, you will use the program that's write by yourself?
Yes.
Of course.
Yes. And usually we Agilent called Agilent IO suite. So yeah, for example, in this case, we want to set 1 voltage. We will send the command for especially these devices. So once you buy this measurement device, it comes with programmer's guide. And programmer's guide tells you what kind of command they have. And once, for example, for setting voltage, the command is volt colon 1.0 or volt colon 0.5. So from this one, first we invoke Agilent IO library suite. And through that, once we invoke that IO Agilent suite, our C program can communicate with this one. So in C program, we will have, for example, for loop from for I equal 0.5 until 1.5 step 0.1, and sweep it and send the command to here and change the supply. And all that kind of program is written by us.
Could you tell us some method to determine the device output impedance?
Determine the output
Define the device output impedance. Yes. Make sure when you measure a device, so you recommend the the under test device output impedance. How to
A method to measure the output impedance of the device.
Oh, output impedance.
yes, output.
Output impedance. How to measure output impedance? Okay. Usually when you simulate, you know the output impedance on simulator. And on the real device, you connect the output to the oscilloscope, which has a 50 ohm impedance. So the oscilloscope input impedance is always 50. And let's say you have 1 volt VDD and output high, then you will see the output voltage here. And if the output voltage is 50 ohm, the output voltage becomes half. And if your output voltage is 40 and 50, so output voltage is 0.5 or something. And from that measurement, you will see the output.
Can you be determine exactly the output impedance? Exactly the output impedance.
Yeah, we can calculate the output impedance.
How
This is 1.0 volt for example. This is our output. This is 50. Let's say this is so we are okay.
Is there any? No, but I get that the Dai asked about the output impedance. Impedance means the complex value.
Complex value.
It means that determine the far, the phase.
I have to measure that, and maybe if you really want to measure the output impedance, you output here. You make this on and measure using spectrum using network analysis. I haven't done that, but we can do. Any other questions?
So regarding the return part of the current, right? You have some measurable. But how can we simulate or analyze it in the EDA2?
Examples?
Can we simulate
EDA2, we often have a ground symbol. So if we only want to measure the campus, maybe you will extract S parameter from the layout. So you have signal lines and ground lines and extract S parameter from the layout by using ADS.
from like